All right, let's get into it. Today, we're going to tear down the mathematical engine that lets robots see through the fog of uncertainty. We're talking about the Kalman filter, the algorithm that turns noisy sensor data into a clear picture of reality.
So here's the game plan. First, we need to figure out how to even talk about uncertainty using math. Then, we'll look at a really cool magic trick with a special kind of math that makes this whole thing possible. After that, we'll walk through the Kalman filter algorithm itself. And finally, we'll see what happens when things get messy, because they always do, and how we can fix it.
Okay, first things first. Before a robot can start figuring out where it is, it needs a way to describe its own confusion. It needs a language for uncertainty. And for that, we're going to use a familiar friend, the good old bell curve.
This is the fundamental problem, right? A robot never knows exactly where it is. There's always some doubt. So how does it hold that idea of, I think I'm here, but I could be a little bit over there, in its computer brain? Well, the answer is to embrace the uncertainty and give it a shape.
And that shape is a Gaussian. We model the robot's belief as something called a Gaussian random vector, or GRV. And this is where things get really cool, because this lets us boil down a whole universe of possibilities into just two things. First, the mean, which is simply the robot's single best guess, and second, the covariance, which is way more than just a number. It's a matrix that describes the size and shape of our uncertainty. It tells us not just how uncertain we are, but how those uncertainties are connected.
Whoa, okay, I know this equation looks pretty intense, but don't let it scare you. All this is, really, is the fancy mathematical recipe for drawing a bell curve, and the only ingredients you really need to care about are these two right here. X hat, that's our mean, our best guess, and P, that's our covariance, our uncertainty. That's it. Those two things define the entire shape of our belief.
And this is where that scary equation becomes something we can actually picture. In one dimension, sure, it's a bell curve. But for a robot in the real world, its uncertainty looks like an ellipse. The dead center of that ellipse is its best guess. The size of the ellipse tells you how uncertain it is. A tiny little circle means, I'm pretty sure I'm right here. A big, stretched out oval means, man, I could be anywhere in this general area.
So you might be wondering, why Gaussians? Why are we so obsessed with this one particular shape? Well, it's because they have a property that is so useful, it feels like a magic trick. It makes all the math downstream not just possible, but incredibly clean. As long as our world plays by one simple rule, it has to be linear.
This right here, this is the whole game. What this means is, if you start with a Gaussian belief and you do something simple and linear, like moving forward 2 meters, the result is another perfect Gaussian. It might have moved, it might have gotten bigger and more uncertain, but it's still a Gaussian. We get to stay in this clean, easy-to-manage Gaussian world.
And check this out. Here's the math that makes the magic happen. The new mean is easy. You just multiply by A. But look at the new covariance. See that APA transpose structure? Some people call it the sandwich rule. You're taking your old uncertainty, P, and you're sandwiching it between the matrix A and its transpose. This is the mathematical operation that perfectly stretches and reshapes our uncertainty ellipse as it moves through the system. Remember that structure because you're about to see it again.
Okay, so we've got all the building blocks. We know how to describe uncertainty with a Gaussian, and we know our magic trick for transforming it. Now, let's put it all together and build the Kalman filter itself. It's really just an elegant two-step dance. Predict, and then update.
To get started, we just need two simple linear equations to describe our world. The motion model tells us how the robot moves. The observation model tells us what the robot's sensors see. And you'll notice both have these little noise terms on the end, W and V. That's us admitting that our models aren't perfect. W is the process noise, our motors aren't perfect. And V is the measurement noise, our sensors aren't perfect either.
So here's step 1 of the dance, prediction. First, we predict our new state. That's the easy part. Then we predict our new uncertainty. And hey, look familiar? There's our magic sandwich rule again, APA transpose. We're just taking our old uncertainty and projecting it forward. Then we add Q, the process noise. This is us basically saying, hey, moving around is a messy business, so I know I'm going to be a little more uncertain than I was before. So our uncertainty ellipse gets bigger.
And now for step 2, the update. This is where the real magic happens. Our robot takes a look at the world through its sensors, gets a new measurement, and we use that piece of data to correct our prediction. This is where we fuse our internal belief with external reality. And because we've gained new information, our uncertainty is going to shrink.
The secret sauce of this whole step is a value called the Kalman Gain, K.
You can think of it as a smart trust knob that's tuned by this equation. It's basically a tug-of-war between your prediction uncertainty, p-bar, and your measurement uncertainty, r. If your sensors are really noisy and r is huge, the Kalman gain becomes tiny, and you barely listen to the measurement. But if you were really uncertain about your prediction and p-bar is huge, the gain gets big, and you say, okay, I'll trust this new sensor reading a lot. It's the mathematically optimal way to blend the two.
So, this all works beautifully. It's elegant, it's optimal, it's perfect for a world that's perfectly linear. But you know where this is going, right? The real world isn't a straight line. Robots turn, sensors measure angles. The real world is messy and nonlinear.
And this right here shows you why that's a huge problem. On the left, in our linear world, everything's great. Gaussian in, Gaussian out. But look at the right. You take a perfect, beautiful bell curve and you shove it through a nonlinear function like sine, and what comes out is this weird, lumpy, distorted thing. It's not a Gaussian anymore. And just like that, our entire mathematical foundation, our whole Gaussian world, completely falls apart.
So, are we stuck? Do we just give up because the world isn't simple enough? No way! This is where engineering gets really, really clever. We need a workaround, a kind of mathematical hack, to deal with the messy real world. And that hack is called the Extended Kalman Filter, or EKF. So what's the big idea? It's actually brilliant. The EKF doesn't even try to solve the hard nonlinear problem. Instead, it cheats. It basically says, okay, I know the world is curvy and complicated. I can't handle that. So, for just a brief moment, I'm going to pretend it's a straight line.
And how does it pretend? With a little bit of high school calculus. It looks at that curvy function, finds our current best guess on that curve, and just draws a straight tangent line right at that point. For one tiny instant, it assumes the world behaves just like that simple straight line. And the slope of that line is calculated using a matrix of derivatives called the Jacobian. This Jacobian then just slots right into our old Kalman filter equations where the A matrix used to be.
So when you put them side by side, what actually changes? Well, to predict the state, we use the true, messy, nonlinear function f. No problem. But to predict the uncertainty, look, it's our old friend, the APA transpose sandwich. Except now A isn't a fixed matrix anymore. It's the Jacobian. The big difference is that our A and H matrices used to be static. Now they're these dynamic Jacobians that we have to recalculate every single step. It's the same dance, just with a lot more calculus.
Look, the EKF is an incredibly powerful tool. It's used everywhere, but we have to be honest with ourselves. It's built on an approximation. It's built on a little white lie that the world is a straight line, at least for a moment. And that leaves us with one final, very important question. What happens when the world is so curvy, so nonlinear, that our little straight line approximation is just wrong? That's where the EKF can fail. And that's where we have to step into an even more advanced world of filtering, with things like the unscented Kalman filter and particle filters. But that's a story for another time.